So very good morning, students. So we were starting with the unit number 1. We have started in last class, what and all is there in unit 1, 2, 3, 4 and 5, and today let us go with unit number 1. So syllabus for unit number 1, we are going to see about power switching device overview, attribute of an ideal switch, then we will go with the power diode today. Okay, then we will see with power handling capability and all. So just let us start. What is power electronics is? This is just a definition saying what is power electronics is. Refers to an interdisciplinary subject within electrical engineering that deals with design, control, conversion of power in its electric form. A system that converts electrical energy to an electric load through a control circuit is known as power electronics. So our role is, it is just a subdivision of electrical engineers. We are designing so many types of converters, and these converters are controlled for varying the power. That is, the power we say is DC or AC. If it is DC, then we might have studied so many converters like buck converter, boost converter and all. So on the whole, to clearly say, depending upon the load requirement, you are going to change your supply. That is what you are doing here. Okay, if I want 12 volt, 10 volt, 13 volt or 50 volts, 100 volts, or nowadays even power electronics we use for 400 volts to 600 volts DC. Okay, from AC we are able to get this DC. So in other words, we can say it is like a transformer in a AC circuit. So what do you do with the transformer? Transformer with the primary and secondary, you are able to step up or step down. So similarly with the power electronic devices, we are able to step up or step down the voltage as well as current as required for the load. Okay, so you will have electrical power, which is input, which is AC power or DC power, whatever may be. Even if you have AC power, then you will have a rectifier block and then you bring to DC. If it is a direct DC itself, then you will have this power electronic circuit is nothing but converters. Okay, so this converter we are able to vary the output voltage and which is required for the load. So all DC loads are not same. For example, even operating your microcontroller, you need DC, but that is very less of 5 volts. And nowadays even we have microcontroller with operating voltages 3.3 volts itself. Okay, so for that also you use this power electronic circuits, and you use it for drive application also. If this replaced by a motor, then by varying the voltage or by varying the frequency, you try to vary the speed of that particular motor. Okay, so in general we can classify. Okay, now why we go for power electronic converters is to get maximum efficiency. See, when you are stepping down or stepping up, power consumption should be less by the converters. So you should have maximum efficiency, maximum reliability. Whenever you switch on, your output voltage or output current should not vary. See, you for a black body approach, you know, I give input, I take output, I don't want to know what is there inside. For example, if you have a mobile phone charger, your charger is there. Whenever you use this charger, you have to get the DC with the fixed DC. The DC should not vary. That is what we call it as reliability. Then maximum availability, wherever you go, you are supposed to plug in that charger and use. See, you are not supposed to say, this charger will not fix to this plug point and all. So it should be of availability, minimum cost, that we all know. So if you are preparing a power supply and you say the power supply cost itself is more, then nobody will buy that particular thing. Then least weight. So this, by introducing power semiconductor device, automatically your size will come down, weight and size will come down. Okay, the application of power electronics is classified into two types. So this is what I am saying. It was static application and drive application. Static is stepping up, stepping down, all that thing, and drive is your motor drive. Okay, so first of all we will see with static application. By the word static itself, we all know that there is no moving part, there is no rotating or any other part, so it is just a power supply. Okay, you will get it AC power supply. If you are able to get AC power supply, then this block is required, diode rectifier. If you are getting DC supply itself, you will not need this particular block. When you will get this AC supply, whenever you get it from grid, whenever you get the input from the grid, obviously grid is AC grid. In India we don't have any DC grid, we have only AC grid. So whenever you take from EB, you will have AC voltage, you need diode rectifier. But when you have installed a solar panel at your rooftop, then the supply will be directly DC. So this two part is not at all required. Diode rectifier and filter is not required, but the thing which is required is DC to DC converter and load. Directly you can give it to DC load, or if you want you can convert it into AC load, where you insert a block called inverter here. And this is entirely, we call it as static, because there is no moving part in it. And you can see that this static, for application of static, we call it as DC power supply. So DC power supply is a static application of power electronic devices. I repeat, if you are taking from TNEB, then the source will be AC. If you are taking from solar, then the input will be direct DC. But the output from solar cannot directly connected to load, because you have to make it as a constant voltage. To make it as a constant voltage, you go for a DC to DC converter. Either you go for boost mode or buck mode, depending upon the requirement you want. Okay, so this is first type of application where we use power electron devices. And the second one is drive application. Drive application nowadays we require, because we go for electric vehicle nowadays. The entire scenario is changing from fossil fuels, let us say petrol and diesel. I am moving towards electrical. Okay, so electric vehicle, if you say, then drive application. So in drive application, what is my power electronics role is, you see here I am explaining with an air conditioned system. In an air conditioned system, the main person is this air condenser. Air condenser is nothing but you will have a particular gas. Let us say in your AC at home, you have a gas called R232. So R32 is the gas. Initially they were using furan like material, but that disturbs ozone. So nowadays we are not supposed to use that gases which are harmful. So we go for a gas called R32. So this R32 gas, what we have to do is, we have to compress. So when you want to compress, I should have a motor. So when I am compressing the gas, what will happen is, its pressure will increase and temperature will fall. So this I will allow inside the room. So temperature of the room will be absorbed by the gas, and thereby it will try to chill your room, and that air gets eaten up. Again you will go for compression, and that process repeats. So to compress I need a motor. So this motor is operated based upon the temperature you set. That is the conclusion. All this I was explaining to say that this is not rotated at the same speed. So the speed of this particular motor is varied. So you will operate this motor at variable speed. To operate this motor at variable speed, I need a power electronics converter. Okay, so if you want to operate in same speed, then nothing is needed. Just give the supply to the motor starts rotating. But that is not the scenario. This inside temperature will be sensed, room temperature will be sensed, and the sensed temperature will be converted into control signal, that based upon the set value, whether you have to continue cooling process or stop the cooling process. That is what closed loop is. If the set temperature is reached, then you will not cool beyond that particular instant, then you will switch off. And if the temperature is rising, then again you will start your temperature cooling process. So you need a person called a power electronics based converter. So here we will have some converter circuit with the firing pulse, and this firing pulse will try to make variable output voltage, and variable output voltage try to make this motor run at variable speed, and this speed will depend upon the cooling effect. Okay, so here I have shown an AC air conditioned system, whereas in nowadays this is your two-wheeler or four-wheeler motor. Okay, so I think even now corporation has went into electric vehicle, no more tricycle. I think you can see at road all corporation vehicles are now electric vehicle. there they doesn't go for BLDC or PMSM. That is only based upon motor system. They will have a reap motor, so that motor will be connected to the wheel. And nowadays technology has developed, you don't want to have a separate motor and a chain drive. So now electrical vehicle and all, the entire wheel of your vehicle itself will have a stator and a rotor. Okay, but whatever you say, I should require a person called a power electronics based converter circuit. For this power electronics based converter circuit, I need power semiconductor device. Okay, without power semiconductor device we cannot do. Power semiconductor devices are like MOSFET and IGBTs, where you give the firing pulse to the MOSFET or the IGBT, and that makes the variable output voltage. Okay, that variable output voltage is given to the motor for the drive purpose. So when you see it for electric vehicle, you say it as drive. Otherwise, like compressor, pumps, conveyor belt, in a factories equipment will be transferred via conveyor belt, where the speed of the conveyor belt can be varied by varying the firing pulse to this power electronics based converter. So basically only two type of application. One is called static application, another one is called drive application. In drive, there are, for industry you have so many drives, as well as you for air condition unit and all such thing, and then you have go for electric vehicle. Okay, then classification of power semiconductor devices are power semiconductor switches. Okay, first one is based upon the number of terminal. So based upon number of terminal, I have 2 terminal or 3 terminal. 2 terminal is nothing but you will have only 2, so there is no controlling. So it is, even you can call it as uncontrolled device, whereas 3 terminal devices are controllable. Okay, so 2 terminal device are the only 2 terminal device which we use in semiconductors is diode. Okay, triode or diode you have. Okay, triode, whose state is completely dependent on external power circuit and they are not connected to it. So what it is we are saying is the turn on and turn off you are not deciding. Turn on turn off is only decided by the external power. So that is 2 terminal device, or these device do not have any control. Then moving into 3 terminal device, whose start is not only depend on external power circuit but also the signal on the driving terminal gate. We call it as gate or base. For some devices we call it as base, and for some devices we call it as gate. Okay, now only if you give the supply to this gate or base, then the device will get turned on, otherwise the device will not be turned on. So external power does not have any influence, only the firing pulse have the influence. Okay, so this is the difference between the 2 terminal and 3 terminal. Then second type of classification is, we classify into the type of carriers. This is most important. You have to understand it clear. There are 2 types of charges. One is called majority charges, another one is called minority charge carriers. So if I take a p-type semiconductor, in a p-type semiconductor, what is the majority charge carriers are? Majority charge carriers are holes, and minority charge carriers are negative in case of p-type material. And similarly in n-type material, the majority charge carriers are, in n, majority charge carriers are electron and minority charge carriers are holes. So what is meant by minority charge carriers? So in case of minority charge carriers, let us take an NPN transistor, NPN. What is the center layer? Which is P. This P is connected to the base, and we have seen that it is a 3 terminal device. So only if you give base, then the device will get on, and for this base I am not giving majority charge carriers. What I am going to give? I will give minority charge carriers, then only that particular type of device will get turned on. So that is called minority charge carrier, people. If it is N, P, N, you might have seen, I will give electrons. So this electron enters the P region, which are minority. If this minority is more than sufficient, automatically electron from N type will pass this P and crosses the N. So the device will get turned on. So, but there is a problem with always with this minority charge carriers, because they cannot be turned off. So you can only turn on and turn off is not possible, because what you told, that fellows minority itself is able to conduct the device, and when the devices get turned on, automatically the N on the both side, they will supply electrons to this P, so you lose the control, and control is gone to the outside, or the what we have seen in number 1. So control has gone to the external power, not from your side. So that is the minority problem. So this minority charge carrier problem has led to majority charge carrying device. So where you face this problem is when you convert AC to DC, automatically your AC goes to 0 after every 10 milliseconds. So this minority charge carriers, the external supply is going to 0. So what I told, you lose the control, only the external supply will have the control. I told in minority, I repeat, in minority, after turning on, you have the power to turn on, but once you have turned on, you lose the control. What I told, the external power as the control I told, this external power control I told. So when this external power itself is going to 0 at every 10 milliseconds, automatically device get turned off. Okay, this is the condition here. But when using these devices with DC supply, then you can see they will not go to 0 at all. Once you turned on, the supply will not go to 0 at all, and the device cannot be turned off. So that is why the reason minority charge carriers, charge carrying based device, we are not using today. So that is why we are going with MOSFET and IGBT. In MOSFET and IGBT, MOSFET is turned on with the majority charge carriers. So when you say majority, whenever you try to remove, then there won't be any majority charge carriers, automatically device will get turned off. So this is second type of classification. And third type of classification, we call it as uncontrolled switch, semi-controlled switch and full control switch. Again the concept is same, only the way of classification we separate. Uncontrolled is, we all know that diode, after voltage crosses 0.6, that is minimum voltage to turn on 0.6, automatically your device will get turned on. Till 0.6 it will be in off. Once the supply voltage is more than 0.6 or the external voltage is greater than 0.6, your device will get turned on. In semi-controlled switches, I have told no, all type of thyristors like your NP, PNP, where you can only turn on, turn off is not possible. Fully controllable is comes all your voltage devices. A small mistake, BJT will not come here, only MOSFET, IGBT, GTO and MCT will come. This two will not come, because this two comes under thyristor family, bipolar junction transistor and junction field effect transistor. This comes under your semi control, not on fully control. Okay, so this is about the classification of your power semiconductor device. Again I told 2 terminal, 3 terminal, only person whose 2 terminal is diode, so that has been written here. In 3 terminal device, I have majority charge carriers and minority charge carriers. In minority charge carriers, there are some device, and majority charge carriers, you have some devices. Then let us go with the brief history. So the entire power electronics was come into picture only after 1952. Okay, then thyristors appeared in 1957. Thyristors are able to withstand very high reverse breakdown voltage and are also capable of carrying high current. Now also, if you have any AC to DC conversion, I repeat, whenever you have any AC to DC, why I am repeatedly saying is, this subject is very useful for your ME project, and UG you might have done your project in a group, whereas in ME you have to separately do the project. There is no group and all, so each and everyone has to separately do the project. At that time it will be very useful. When you go for any rectifier application, then you are supposed to use only thyristor, because thyristor can withstand very high reverse breakdown voltage and capable of carrying very high current. So we go for thyristor. One disadvantage in thyristor, that is what I have already told, you cannot turn off. Only latch on, latch off is not possible, or you cannot turn off. But no problem, you use this in AC to DC conversion, that is from AC to DC conversion. Thyristors are more useful, because automatically the supply will go to 0, so automatically your device will get turned off. Then first bipolar transistor was developed in 1960. Then comes an improvement in metal oxide field effect transistor. So 1970. So till 1970, power semiconductor device or converters are not came into picture. Only after 1970 the converters came into picture, like buck converter, boost converter, buck boost converter, tube or SEPIC, all type of converters came into picture only 1970. So okay, 1970. Now we are in 2021. Okay, so this is the period where the power electronics came into picture. So everything became small. Okay, all your appliances became small. Initially, since you don't have this person, your TV and all was very huge in size, your display units and all very big, even your computers were very big, and after this fellow everything size has get reduced. Then comes your insulator gate bipolar transistor. So this was developed in 1980 and widely now available in 1990s, and now IGBTs are used for all the applications. So that is about the briefing about your various types of power electron devices used in as in your converter circuits. Now let us go for what is a switch. So now we are using you might have studied in undergraduate electronic circuits, where I use the device for switching as well as amplification. You might have read it, common emitter, common base, common collector, in which one configuration you use for amplification purpose. And now totally forget about all that thing, because now we use the switch only to turn on and turn off, or in other words, all power semiconductor device are going to use only as a switch. Here we doesn't talk about any amplifier and all. So now ideal switch, if you take, when the switch is off, you will have maximum voltage, minimum current, or the current is zero. Okay, when the switch is turned on, when the switch is closed, automatically voltage becomes zero, current becomes maximum, and again when you switch off, what will happen is voltage will be maximum, current will be zero. Now for an ideal case, you can see at the instant when you turn on, this is the instant where your switch is turned off. Once your switch is turned off, there is no surge or there is no delay in time. Straight away your switch, across the switch you will have maximum voltage, and this is the place where I am switching on. So if I switch on, there is no time delay or time taken. Suddenly voltage reaches zero, and at that instant suddenly current also reaches maximum. This is possible only in case of an ideal switch, because no person can be operated with zero operating time. See, for example, if you take our case, when anything, if it is been told, it has to go to brain and it has to accept, and then you will do the work. Because since you may think, sir, I am little bit fast. We are fast because we have learned the language. To a newborn baby, if you say whether it will be able to do, no, because you have learned the language and you are able to understand the language. Based upon the language, you try to identify what the opponent is speaking, you will respond for it, but it takes some time, but it is very less, that's all. Okay, so when you take power, here V is there, I is not there, so power is zero. Here I is there, V is not there, power is again zero. Here your V is there, V is there, I is not there, power zero. So in an ideal switch, power consumed across the switch is zero. Don't think that power is zero. See, when you on the switch, automatically there will be flow of electron. This electron is going to the load, where load consume power. Switch does not consume any power. I repeat, by seeing this diagram you don't get confused. Sir, you have not drawn power at all, because for an ideal switch does not consume any power. Ideal switch is not consuming power, because see here, when voltage is there, current is zero, power is V into I, zero. When voltage is not there, when current is there, again V is zero, so V into I, again it is zero. Again you see here, it is similar to the case 1, where current is not there, voltage is there, voltage multiplied by 0, it becomes 0. So power consumed across the switch is 0, so there is no loss. When you design a rectifier using an ideal switch, there won't be any power consumed by your device, the rectifier. But when you come with a practical application, your switch is made up of semiconductors, so they consume some little bit of power, and the power will be dissipated in the form of heat, because they are not conductor. Once if you say conductor, they won't offer any resistance. If they are not offering resistance, then nothing is power consumed. But when you say ideal case, it doesn't consume power, so V and I here again it becomes 0. So switch is not consuming any power. I am repeatedly saying switch is not consuming any power. Don't think load is not consuming any power. Load will be after the switch. You will give supply to the switch. From the supply it will goes to load, and load will consume, and there you will have power consumption, but across the switch is 0. Now let us go to practical case. In practical case, let us go step by step. So initially take, if you want to take notes, take it as at initially the switch is in off. When initially switch is off, which means you will have maximum voltage and minimum current. Why this minimum current is there is, there are some devices which are conducting due to minority charge carriers. If there is minority charge carriers, even the device is off, some minority charge carriers will be flowing across the device. See, from this end to this end, even though switch is open, these are made up of semiconductors, and this region may have some minority charge carrier, and that is flowing here. So once you turn on the device, the voltage slowly reduces and reaches the minimum value, and this is the time taken for the voltage to reach 0. Similarly, current will enter the semiconductor, and slowly it will start picking up and reaches the maximum value. So at this instant, if you see, there is simultaneous existence of V and I, and this is loss called as switching loss. So loss when occurring due to switching, and then this will reaches a minimum value, and this reaches a maximum value. Again this will not reach as 0 because of semiconductor property. So now V is not 0, you have more amount of I, multiply by this, you will have some amount of loss. This we call it as on state loss. So this is called switching loss, this is on state loss. Put together we will say it as total loss or conduction loss. Similarly, when the device is when you are turning off, voltage will slowly pick up and current will slowly drop. At this part of the time, you will have some amount of power consumed by the switch. So this bottom line what I am drawing is power consumed by switch, not your load. So if the power is not consumed by the load and consumed by switch, then it is only loss. So this is the practical switching case. So this might be, if your end semester is a normal way of writing with the 16 mark question and all, then they will ask, explain the ideal characteristics of a switch and the practical characteristics of a switch. If they ask, it may be asked in 16 mark, then you have to explain each and every step. Okay, you have to say what is this part, and what is this part, and finally what is this, and what is this particular region. So this is called switching loss, and this is called on state loss. Put together we will say conduction loss. Okay, so these losses are it's nothing but electron which is converted into heat, and you will feel the heat across the semiconductor device. Then switching strategy. Okay, when I say on or when I say off, let us see for ideal case. When you see for ideal case, if I say on, at this instant if I say on, sharply it will increase to this value and remain in on. If I say off, at this instant it will suddenly fall to 0. So this is off. Similarly, if now I am in off state, if again I am asking him to on, it will go to maximum value, stay in the maximum value, and if I say off, it will go to 0. So you can see here it is a perfect case for an ideal switch. I again repeat, for an ideal switch, I am staying at this particular instant and I am saying on. Current will reach us maximum at that instant itself and stay in the maximum itself till I say off. So that is the condition. So you can draw it by a line like this. When you say on, on. When you say off, off. But if load is inductive, then this will be the value, and load is resistive, this is the value. But typically practical waveform, what will happen is, if I am standing here, I am say off, it will go to overshoot, then it will start to decrease, that is current. Suddenly I cannot make current to 0. I think you all know. In a practical case, what we say, in a practical circuit where there is inductor capacitor, if I suddenly turn off, current will not go to 0 directly. There will be a overshoot in current. That overshoot in current, then current waveform will slowly come to 0. And again when I on, it will not directly go to on state, it will have a transient, it will try to reach its maximum value. So this is the switching strategy for ideal, for inductive, then for practical case, and for resistive. So all the 4 types they are mentioned here: inductive, resistive, ideal case, and practical case. Practical case, you have both resistance and inductance, that makes the delay. Okay. Then let us move on to the first type of device today, that is power diode. I think you might have done project in UG with some diodes, and that diode and all you say it as normal diode, and this is called power diode because the power level is have to be increased, so you should have more current carrying capability. So you go for power devices. So like this only it will appear, either like this or it will be like a mesh at one end. This is usually here we connect positive and this we connect negative, okay, or in some case. So this is your diagram. So we all know that anode is P type and cathode is N type. So conduction can be possible only from anode to cathode. Only this direction is allowed, this direction is not allowed. So an ideal diode should have the following characteristics. When forward biased, the voltage across the N terminal of the diode should be 0. Really it is not possible, whatever the current that flows through. When reverse bias, leakage current should be 0, whatever voltage, then the transmission between on and off state should be instantaneous. All this is for ideal, which is not actually possible. Okay, so this is the symbol and this is the VI characteristics, and these are the some practical power diodes screenshot. Now we move on to practical power diodes where static parameters. Whenever you say static, we talk about VI characteristics. VI characteristics is a static characteristics. Okay, so when I am turning on, after this voltage, my voltage starts to build up. Okay, your current starts to build up, and that is what we say is minimum voltage, and this voltage will be there across the device when the device is on. Okay, so that we call it as forward voltage, V suffix F. Similarly, when your devices get turned off, there should not be any current, but some current will be flowing. That current is called as reverse. This forward current is called IF and reverse current is called IR. So here when the device is turned on, you will have minimum voltage and you will have maximum current, and this current I call it as IF, forward current. And when there is reverse bias, there will be some current which is called as reverse current, and this is instant, beyond which if I try to increase the voltage, device will get breakdown, and this voltage we call it as V suffix B. So these are the values which are there to represent your static parameters. When you go for dynamic parameter, forward recovery time. Forward recovery time is nothing but previously the diode was in reverse bias, and if I am bringing from reverse bias to forward bias, what is the time taken? That we call it as forward recovery time. Reverse recovery time is now the device is in on, I am reversing the polarity. If I am reversing the polarity, device has to go to reverse bias condition, and the instant it takes to reach the reverse bias from the forward bias condition, that is called this reverse recovery time. So this is that instant. At this instant, what I mean to say, I am turn off the device, which means current is 0. So now what will happen is, it will not stop here, current will start reducing and it will not stop here, it will go in negative direction and then it will slowly come to 0, and this time is called as reverse recovery time. We call it as TRE. Then peak reverse recovery current, which is the maximum current which is flowing in opposite direction, that should not flow but it is flowing in opposite direction, and their magnitude we call it as I suffix RR. Then diode capacitance CD, this is due to this effect. once the current has touched 0, it should stop at this particular instant. But why it is not stopping? The circuit has some capacitance. That capacitance will try to discharge, and this is the discharge time of the capacitance. It is trying to discharge and reach the maximum of the reverse direction. Okay. So that is, we call it as diode capacitance, and the rate of voltage and current we call it as di by dt. So rate of change of current with respect to time and rate of change of voltage with time, this we will observe when the device is from off to on, and this we will observe when the device is from off to on. This is on to off, this is off to on. Okay. Then transient terminal resistance, high frequency, this is the resistance offered by the device during the switching period. Now let us move on to diode protection. Since see here, the diode is turned on, and if you are trying to turn off, due to the circuit capacitance there is a reverse flow, and that will try to break the device. In order to avoid this, what I will do is I will put a parallel path, and this parallel path is like a snubber. So instead of making it to flow across this, we will make it to flow across this, and automatically it will be lost in the resistor in the form of heat. Now this resistor can get heat up, my device should not get turned up, heat up. So that is why I put a snubber circuits. Okay, this is one type of protection. And next type is, see, the voltage between these two terminal is very high. Let us assume 1500. So single diode cannot withstand. So we will go for paralleling method or seriesing method. In series, you can see the total voltage Vs is distributed across the diode D1, D2, D3. Okay. So for each and everything, I have a separate snubber circuit. So this snubber circuit will protect my device. So diode rating. So when you go for purchasing a diode, you should go for voltage rating and current rating. Once the respective peak, reverse, inverse voltage. So voltage rating you will see only when the device is connected in reverse bias. After this class, I will explain why you want to go for voltage rating and current rating. So voltage rating is nothing but repetitive peak inverse voltage, that is VRRM. The other non-repetitive peak inverse voltage. All this you have to see and then consider for your circuit. Similarly, current rating. So just I have put in a screenshot of 50 amps diode rectifier. So this rectifier is capable of observing around 50 amps. So thank you, students. So with this we will stop. Now we will go for